We start a new topic, RF oscillators. Oscillators are nonlinear circuits that convert DC power to an AC waveform. Most RF oscillators provide sinusoidal outputs. Oscillators are realized using diodes and transistors. Apart from diode and transistor based oscillators, crystal oscillators are also used, which provide better frequency stability. So, in this lecture we briefly discuss some of the characteristics of the oscillators. We will start our discussion with some basics of oscillator design, and those concepts will be applicable to oscillators operating in the lower RF frequencies, and then we will discuss some issues related to the design of oscillators for the microwave frequencies. The figure shows the basic block diagram of a sinusoidal oscillator. Here we can see that V output is multiplied by h omega, the gain of the feedback path, and then it is added to V I. Now, this is a positive feedback circuit. So, V I plus V naught H, this is multiplied by A, and that becomes equal to V naught. So, from there we can write V naught omega is equal to A divided by 1 minus A H omega V I omega. So, if the denominator becomes 0 at a particular frequency, it is possible to achieve a non-zero output voltage even for 0 input voltage, and thus the circuit actually forms an oscillator. This condition that 1 minus A H is equal to 0, this is known as Nyquist criterion or Barkhausen criterion. Now, the RF oscillators can be designed based on BJT or FET. There can be various configurations such as Hartley, Colpitts, Clapp, Peirce. So, we will discuss a generic block diagram where this active device, this terminal can be the base, this can be collector, and it can be emitter if the device is a BJT. In case of a FET, this terminal is the gate terminal, this is drain terminal, and this is source terminal. We have a feedback network which usually comprise of reactive elements which are represented as Y1, Y2 and Y3. Now, feedback is provided by connecting this V3 and V4. So, here what we do, we first carry out a analysis, nodal analysis. So, here if you consider this node, we can see that V1 minus V2 into Y1, V1 minus V 2 into G I and V 1 minus V 3 into Y 3, sum of this must be equal to 0 by KCL. If we consider this node and apply KCL, then the currents, sum of the currents given by V 1 minus V 2 into Y 1, V 1 minus V 2 into G I, V 1 minus V 3 into Y 3, sum of these currents must be equal to 0, and we can carry out this analysis for this node, voltage node 1, 2, 3, 4. So, for this first node, as we have seen, Y 3 V 1 minus V 3 plus Y 1 V 1 minus V 2 plus G I V 1 minus V 2 equal to 0. So, when it is rearranged, we can write Y 1 plus Y 3 plus G 1 into V 1 minus Y 1 plus G I into V 2 minus Y 3 V 3 equal to 0. So, when this analysis is carried out for all other 3 nodes, we can write the complete matrix in this form. Now, we know that if the ith node of the circuit is grounded, the ith row and column are eliminated, reducing order of the matrix by 1. And similarly, if 2 nodes are connected together, we have said that in our reference figure, we need to connect V 3 and V 4 to provide feedback. Then the matrix is modified by adding the corresponding rows and columns. So, let us now consider an oscillator circuit using a common emitter BJT. Now, in this oscillator using BJT, we will operate the BJT in CE configuration, and in this case we will have V 2 equal to 0 with the feedback provided from collector. So, V 3 is equal to V 4, and in addition the output admittance of the transistor is considered negligible. That means, we have G naught equal to 0, and let us represent V equal to V 3 equal to V 4. So, if we now refer to our this matrix, when V 2 equal to 0, this second row and this column will be eliminated, and when the nodes 3 and 4 are connected together, and also we have G naught equal to 0, then if we add these rows and columns, essentially these values will not change. Y 3 minus Y 3, Y 2 plus Y 3, they will remain as it is, and in that process now this matrix will essentially be reduced into a 2 by 2 matrix. Please note that we have put V 3 equal to V 4 equal to V. If this circuit is to operate as an oscillator, then we must have non-zero values for V 1 and V, and in order to have this, the determinant of the matrix must be 0. As we have said that y 1, y 2, y 3, these are reactive elements. Let y 1 be j b 1, y 2 be j b 2 and y 3 be j b 3. So, substituting this y 1, y 2 and y 3 here, we get this particular determinant has to be 0. Now, equating the real and imaginary parts to 0, we get the relation 1 by B 1 plus 1 by B 2 plus 1 by B 3 equal to 0. And 1 by B 3 plus 1 plus G m divided by G I into 1 by B 2 equal to 0. So, these are the two relations we obtain. Now, if we substitute x 1 is equal to 1 by B 1, x 2 is equal to 1 by B 2 and x 3 is equal to 1 by B 3, we have x 1 plus x 2 plus x 3 equal to 0. And also we get, after substitution in the second equation, x 1 is equal to G m by G I x 2. Now, here G m by G I, this will be a positive quantity and therefore, x 1 and x 2 will be of the same sign. Now, if we choose x 1 and x 2 to be capacitors, in that case x 3 has to be an inductor, because x 1 and x 2 has the same sign and x 3 must have a sign opposite to x 1 and x 2. And this particular configuration, when we have x 1 and x 2 are capacitors and x 3 is an inductor, this particular configuration is called Colpitt's oscillator. And from this relation, now we can write minus 1 by omega naught 1 by C 1 plus 1 by C 2 plus omega naught L 3 equal to 0. So, here omega naught is the frequency of oscillation where this relation is satisfied, and solving for omega naught we get the frequency of oscillation, which is given by under root 1 by L 3 into C 1 plus C 2 divided by C 1 plus C 2. So, this omega naught is the frequency of oscillation of the circuit. Also, from this relation x 1 is equal to G m by G I x 2, we can see that the necessary condition for oscillation of the Colpitt circuit is C 2 by C 1 is equal to G m by G I. When x 1 x 2 are inductors, and X3 is a capacitor, we have a Hartley oscillator, and this condition x1 plus x2 plus x3 equal to 0 will now give omega naught L1 plus omega naught L2 minus 1 by omega naught C3 is equal to 0, and omega naught can be found out as under root 1 by C3 into L1 plus L2. Again, from the relation x1 is equal to Gm by Gi x2, we can find that condition for oscillation for the Hartley oscillator circuit is L1 by L2 is equal to Gm by Gi. So, the basic form of Colpit oscillators is shown here. So, we have a common emitter BJT, and we can see that the feedback is applied from the collector, and we have this Y1, Y2, Y3 represented by C1, C2 and L3. These are the biasing resistors to ensure that the transistor is biased in the active region. Similarly, for the Hartley circuit, we have once again the feedback goes from the collector. These are the biasing arrangements, and the reactive elements are L1, L2 and C3. Now, both the circuit configurations provide positive feedback, which is necessary for the operation of an oscillator, and the frequency of oscillation is decided by omega naught for both the circuits, and the oscillation frequency can be set by proper design of the inductors and the capacitors. So, transistor based oscillators, what we have discussed, these are useful for RF frequencies, but when the frequency becomes very high, in the higher microwave frequencies, the oscillator circuits, they employ negative resistance diodes and transistors. So, the device is operated in the negative resistance region. We show a generic representation where a canonical RF circuit is shown as one port negative resistance oscillator, and we have a device where this Rin is negative. Now, as we have already discussed while discussing the devices, that negative resistance here implies the generation of RF energy, whereas when the resistance is positive, it dissipates the energy. Now, if you consider this circuit, we find that Zin, which is equal to Rin plus J Xin, it is the input impedance of the active device. And since there is no other generator here, we will have ZL plus Zin into I equal to 0, where I is the loop current So, if we have oscillation occurring in this circuit, then we will have RF current I is non-zero, and therefore, we have Z in plus RL equal to 0, and if we separate the real and imaginary part, then we get RL plus Rin equal to 0 and XL plus Xin equal to 0. Since RL is a passive load and therefore, it is greater than 0. So, this condition is satisfied only if Rn is less than 0. Now, ZL is equal to minus Zin for steady state oscillation. It implies that gamma L, which is defined as ZL minus Z0 divided by ZL plus Z0, can be written as minus Zin minus Z0 divided by minus Zin plus Z0, and this can be written as Zin plus Z0 divided by Zin minus Z0, which is essentially 1 by gamma in. The process of oscillation is critically dependent on nonlinear behavior of Zin. Initially, it is necessary for overall circuit to be unstable at a certain frequency, so that Rin as a function of I and omega plus RL, this becomes less than 0. Any transient excitation or noise, now this is how the start of oscillation is usually described. So, any transient excitation or noise causes an oscillator to build up at the frequency omega. As I increases, Rin I j omega must become less negative until the current I naught is reached such that Rin as a function of I naught and omega naught plus RL is equal to 0, and similarly Xin as function of I naught omega naught plus XL function of I naught omega naught is equal to 0. At this point, the oscillator can run in a stable state. The final frequency omega naught generally differs from the startup frequency, because Xin is current dependent and Xin I omega is not same as Xin I naught omega naught. Now, we have seen how oscillation can start and it can become stable at some frequency omega naught. Now, stability requires that any perturbation in current or frequency will be damped out. So, a small change in the current or frequency, it will be damped out, allowing the oscillator to return to the original value, and this condition can be quantified as del of XL plus Xin del of omega much greater than 0, and essentially this translates into the fact that a high Q circuit results in better oscillator stability, and that is the reason why cavities and dielectric resonators are used for this purpose. So, when we use a transistor for designing microwave oscillators, we have the transistor, and in the input side now we have a terminating network, and we also have the load network. Zin is the input impedance looking through these transistor ports, and corresponding reflection coefficient is gamma in, and gamma s is the reflection coefficient looking into the terminating network. Similarly, gamma L is the reflection coefficient looking into the load network, and gamma out is the reflection coefficient that is looking through the output ports of the transistor. Typically, common source or common gate FET configurations are used. In case of BJT, it will be common emitter or common base, and often with positive feedback to enhance the instability of the device. For steady state oscillation at the input port, we must have gamma in, gamma s is equal to 1, and similarly gamma L, gamma out is equal to 1. This brings us to the end of this module. In this module, we have briefly described the methodologies that are adopted for design of microwave frequency transistor amplifiers. We have seen the particular cases when we design for maximum gain, when we design for specified gain, and we have also discussed very briefly the low noise amplifiers, and finally the oscillators. In the next module, we will discuss microwave frequency tubes, which are still very much in use as high power microwave source. Specialized tubes had to be developed for working in the microwave frequency range. We will discuss the limitation of conventional tubes such as triode or pentode, and then we will discuss specialized microwave tubes such as klystron, reflex klystron, magnetron, and travelling wave tube.